of nature are but the mathematical thoughts of God. And this is a quote by Euclid of Alexandria, who was a Greek mathematician and philosopher who lived about 300 years before Christ. About the quote, regardless of your own views of God, whether or not God exists, or the nature of God, it says something very fundamental about nature. That math underpins all of the laws of nature, and the word geometry itself has Greek roots. Geo comes from the Greek for earth, and metry comes from the Greek of measurement. This is the picture of Euclid, painted by Raphael. No one really knows what Euclid looks like when he was born or when he died. So this is just Raphael's impression of what Euclid might have looked like when he was teaching in Alexandria. Euclid is considered to be the father of geometry, not because he was the first person who studied geometry, but what made Euclid the father of geometry is really his writing of Euclid's Elements, and what the Elements were essentially a 13-volume textbook, and arguably the most famous textbook of all time. And what he did in those 13 volumes is he essentially did a rigorous, thoughtful, logical march through geometry and number theory and also solid geometry. And this right over here is the front piece of the English version or the first translation of the English version of Euclid's Element. And this was done in 1570, but it was obviously first written in Greek, and then during much of the Middle Ages, that knowledge was shepherded by the Arabs and it was translated into Arabic, and then eventually in the late Middle Ages translated into Latin, and then obviously eventually English. And when I say that he did a rigorous march, what Euclid did is he didn't just say, I think if you take the length of one side of the right triangle and the length of the other side of the right triangle, it's going to be the same as the square of the hypotenuse. All of these other things, and we'll go into deep about what all of these things means. He says, I don't want to just feel good that it's probably true. I want to prove to myself that it is true. And so what he did in Elements, especially the 6 books that are concerned with plane geometry in fact, he did all of them, but from a geometrical point of view, he started with basic assumptions, and those basic assumptions in geometric speak are called axioms or postulates. And from them, he proved. He deduced other statements or proposition, or these are sometimes called theorem. And then he says, now I know if this is true, and this is true, this must be true. And he could also prove that other things cannot be true. So then he could prove that this is not going to be the truth. He didn't just say, every circle I've said has this property. He says, I've now proven that this is true. And then from there, we can go and deduce other propositions or theorems. And we can use some of our original axioms to do that. And what's special about that is no one had really done that before, rigorously proven beyond a shadow of a doubt across a whole broad sweep of knowledge. So not just one proof here or there, he did it for entire set of knowledge that we're talking about, a rigorous march through a subject so that he could build this scaffold of axioms and postulates and theorems and propositions. And essentially for about 2,000 years after Euclid, so this is unbelievable shelf life for a textbook. People didn't view you as educated if you did not read and understand Euclid's Element. And Euclid's Element, the book itself, was the second most printed book in the Western world after a Bible. And this is a math textbook. What we're going to study is we're going to think about how do we really tightly, rigorously prove things. We're essentially going to be in a slightly more modern form, studying what Euclid studied 2,300 years ago, to really tighten our reasoning of different statements and being able to make sure that when we say something, we can really prove what we're saying. This is really some of the most fundamental real mathematics that you will do. Arithmetic was really just computation. Now in geometry, and what we're going to be doing is Euclidean geometry. This is really about what math is, making some assumptions and deducing other things from those assumptions.
The opposite side and angle of any parallelogram are equal to each other and the diagonal divide into two equal parts. Let ABC be a parallelogram whose diagonal is AC, then will be opposite sides and angles be equal to each other, and the diagonal AC will divide into two equal parts. Since the side AD is parallel to side BD and the right line AC intersect them, and angle DAC will be equal to the alternate angle ACB. And because of the side DC is parallel to side AB and AC intersect them, the angle DCA will be equal to alternate angle CAB. Since the two angles DAC and DAC are equal to the two angles ACA and CAB each two side, the remaining angle ADC will also be equal to the remaining angle ABC, and the whole angle DAB to the whole angle DCB. But triangle CDA and ABC being mutually equivalent and having AC common, and the side DC will also be equal to side AB, the side AD and the side BC, and the two triangles will be equal in all intersect. Right lines joining the corresponding extreme of equal to and parallel line right line are themselves equal and parallel. Let AB and DC be two equal and parallel right lines, then will be the right lines AD and BC, which join the corresponding extreme to those lines. Be also equal and parallel, for draw the diagonal or right line AC. Then, because AB is parallel to DC and AC intercept them, the angle DCA will be equal the alternate angle, and because AB is equal to DC, AC is common to each of the triangle ABC and ADC, and the angle DCA equal to the angle CAB. The side AD will also be equal to the side BC, and the angle DAC to the angle ACB. Since the right line AC intersect the two right lines AD and BC and make the alternate angle equal to each other, those lines will be parallel. But the line AD has been proved to equal to the line BC. Consequently, they are both equal and parallel. If a parallelogram and a triangle stand upon the same base and between the same parallels, the parallelogram be double the triangle. Let the parallelogram AC and the triangle AEB stand upon the same base AB between the same parallels AB and DE, then will be the parallelogram AC will be double the triangle AEB. For join the points B and D, then will be the parallelogram AB be double the triangle ADB, because the diagonal DB divides it into two equal parts. But the triangle ADB is equal to triangle AEB because they stand upon the same base AB and between the same parallels AB and DE. Hence, the parallelogram AC is also double the triangle AEB. If the base of the parallelogram will be half that of the triangle, or the base of the triangle be doubled that the parallelogram, the two figures will be equal to each other. Its opposite sides equal to two given right lines and one of its angle equal to a given recite line angle. Let AB and C be two given right lines and D is a given right line angle. It is required to make a parallelogram that shall have its opposite sides equal to AB and C and one of its angles equal to D. At the point A in the angle AB, pick the angle ABF equal to the angle D, and the side AF is equal to C. Also, make AFE parallel to equal AB, and join BE, then will be AE be the parallelogram required. Since FE is parallel and equal to AB, AB will be parallel and equal to AF. Hence, the figure AE is a parallelogram, and because AF is equal to C, BE is also be equal to C, and the angle BAF was made equal to angle D. The opposite side of the parallelogram in AE are therefore equal to the two given lines AB and C, and one of its angle is equal to the given angle D as was to be done.
Good day everyone, I'm Kadjem Andal from 2K BSED Math. Now, I'm going to discuss about Euclidean theorem. Then, mag-proceed tayo sa theorem 5.5 hanggang 5.8. Kasi yung theorem 5.1 hanggang theorem 5.4 is na-discuss na ni Miss Caballes. So, this is theorem 5.5. Theorem 5.5 is if a quadrilaterals diagonal bisect each other, then it is a parallelogram. Given a quadrilateral whose diagonals bisect each other, we want to show that it is a parallelogram. We know from the theorem 1.13 that angle ABC is congruent to angle DBE. Notice that triangle ABC and triangle EBD, we know that DB is congruent to BA. Angle angle DBE is congruent to angle ABC, and BE is congruent to BC. Thus, by angle ABC is congruent to triangle EBD. This means that CA is congruent to DE. Without a loss of generality, a similar argument can be made for AE is congruent to CD. By this theorem 5, the quadrilateral is a parallelogram. Now, I'm going to discuss Theorem 5.6. Theorem 5.6 is the converse of Theorem 5.1. Ouch! If a quadrilateral is a parallelogram, then it has both pairs of opposite side congruents. Given a parallelogram, we want to show that both pairs of opposite side are congruent. Start by using axiom 1, constructing line AB. Notice that triangle ACD and triangle ABD. We know that angle BAC is congruent to angle ABD. Then angle CBA is congruent to angle DAB, and AB is congruent to AB by reflexivity. Thus by angle side angle, triangle ACB is congruent to triangle ABD. This means by CPTC, line AC is congruent to DB, is congruent to line DB, and also line AD is congruent to line CB as desired. Theorem 5.7. The converse of Theorem 5.3. If a quadrilateral is a parallelogram, then both pairs of opposite angles will be congruent. Given a parallelogram, we want to show that both pairs of opposite angles are congruent. Since it is a parallelogram, we know from the theorem 5.6 that GH is congruent to GI. We also know that triangle HIG is congruent to triangle JIG. This means that by corresponding parts of congruence, triangle are congruent. Angle GHJ is congruent to angle JIG. It is also means that by CPCTC, angle IGJ is congruent to angle HJG, and angle GJI is congruent to angle JGH. Thus, using common notion 1, we see that angle JGH plus angle GJI plus angle HJG or that angle HGI is congruent to angle IJH. Thus, both pairs of opposite angles are congruent. Theorem 5.8. The converse of Theorem 5.1. If a quadrilateral is a parallelogram, then its diagonal will bisect each other. Given a parallelogram, we want to show that its diagonal bisect each other. Notice triangle ABC and triangle DCE because AB and ED. Theorem 2.3 tells us that angle DAB is congruent to angle ADE and angle DEB is congruent to angle ABE. We also know from Theorem 5.6 AB is congruent to AD. Thus, by angle side angle, triangle ABC is congruent to triangle DCE. This means that by CTC, we know EC is congruent to CB and CD is congruent to AC, which by the definition of a bisector, which the diagonal bisect each other side.